Okay, so today we're going to start MSc form, the 5th chapter, which is going to be quantum algorithms. With basically our we're going to see basically two algorithms, but we're going to see them in different guises. So the first series of algorithms is going to be based on the quantum Fourier transform. So this is a kind of discrete Fourier transform, and we can define it on any old complex space. So imagine we have a n-dimensional complex space. So we have the quantum, the Fourier transform. So the Fourier transform defined on, let's say, C capital N with orthonormal bases. And now we're going to make use of our notation just for a normal vector space. So the Fourier transform is defined as is the linear map and it will take a vector, let's say x, j, j. And we're going to sum both over k and j to e to the 2 pi I kj divided by n. So there's complex roots of unity here with the k. And to be normalized, it we need to put 1 over the square root of n here. Now, of course, in our complex space, we have n qubits, so our dimension is 2 to the n. So in the quantum version.
One question.
Yeah.
Where does the x go? The x of j?
Oh, sorry. Yeah.
Okay.
That makes. Thank you. And so the quantum Fourier transform. We have as n being 2 to the n. And that's a reflection of the fact that our Hilbert space is on n qubits. Okay, so what we've been doing then for our j is we would write j as j1. So as before, we write j as an x binary string. So this would be j1 to jn, where there's the sign. What names have I given it? JL. Well, let's write it out. That makes the much as a sign. So this where this JB. Which is J. This should be a 1. Okay, so that's going to be that's as we had before, yeah. So we would write our basic elements as strings of 0 and 1, then n, which will correspond to the n qubits. Now, what's useful here is we're going to introduce a binary decimal point in the same way that we would have a binary decimal point, as opposed to a decimal point over base 10. So maybe it should just be a binary point. So 0 point, let's say, Jn is Jn divided by 2. In the same way as 0.3 is 3 divided by 10, 0 point something is going to be that thing divided by 2. And then we would have what was 0 point Jn minus 1 Jn. That would be this divided by 2 plus this divided by 4. Okay, so we could write that as 2 times Jn minus 1 plus Jn divided by 4. Okay, so in that way you can write out numbers between 0 and 1 as binary expansions. Maybe infinite. And if we go on here, we get to 0 point J1 up to Jn. Well, that's going to be all of this. So this is going to be J divided by 2n, which we can verify is the sum of JL 2 to the minus. Okay, it's just actually dividing here all the terms of this sum by 2 to the. Okay, well, this notation is useful because it now allows us to write this this quantum Fourier transform in a different way. So the key problem we have with this is now that we have an exponential, this n is 2 to the n. So we have an exponential, 2 exponential sums here. So if we wanted to try and compute this directly, that's going through 2 to the 2n terms, and that's going to take us a while. So the idea is that we can cut this work down with the following lemma. Let's just leave that there for the moment. Oh no, it's a theorem. The following theorem. So let's just see where J goes. So just include J, and the other bit will be extending it linearly. This is going to go to 1 over square root of n, 0 plus. Now we've got to get these things right. So it's starting from this end and going that way. So it's 2 pi I 0 point Jn. 1 times 0 plus e to the 2 pi I, and I've got 0 point Jn minus 1 Jn 1. All the way right down here again, where we've got e to the 2 pi I 0 point Jn1 Jn 1. So that would be just taking xj equals to 1 here, So let's do that then. So that we can use that as the first bit of our proof. So we use proof. We know that J goes to x goes y. The other's all 0, so we can get the k equals 0 of this. And we need to show these two expressions are the same. So let me write this 2 to the n now in here. Put all these, so it's square root of 2 to the n. And 2 to the n there. So this 2 to the n, this k divided by 2 to the n here, we then use this expression, well, this expression here, where j replaced by k. Okay, so the idea now is I'm going to replace these k's with k1 to kn. Okay, so let's just leave that there for the moment. Maybe that may help us. So here we have this is equal to 1 over the square root of 2 to the n. Now I want to write, I'm going to write this k as k1 kn. And so here, instead of summing over k, I need to sum over k1 goes from 0 to 1. K2 goes from 0 to 1. All the way kn goes from 0 to 1. Okay, so that's exactly the same. Now I figured I wasn't going to have enough room. Let's go and one more. Here we have this e to the 2 pi I. The k divided by over j was j, the sum of kl 2 to the minus l here, brackets around there, and then k1 kn. But now you see, we can split these in our individual qubits. So thinking of these as particles, we then write this as in their individual terms. Taking out the k0 bits, we have e to the 2 pi I j k1 2 to the minus 1. And do I want to run those now? Yeah, 2 to the minus 1 times k1. And now the sum over k2. And this is always k. We're almost there because all we have to do now is observe that, well, we just have to write out this sum. This sum is going to give us this 2. Okay, because k is 0, so k1 is 0, so here, that's just going to give us a 1 and a 0 here. And the k1 is 1, so, well, that's not an equation. Yes, okay. So let me now let me write this, and so this is now equal to 1 over the square root 2 to the n. So now I have a product from L goes from 1 to n of, in each case, when the k1's, the k's are 0, I just get a 1 here, e to the 0. And if not, then I get an e to the 2 pi I j divided by 2 to the, this is L is 1, L is 2, up to L is n, so divided by 2 together. Okay, so this is my term corresponding to L is 1 here. I've got, let's just go through that again here. So let's see, when k is 0, this is just 0, this is 1 times k 0. And when k1 is 1, this is 2 pi ij divided by 2 times k1. Okay, and now the L is 2 term, the L is 2 term is this term. So when k2 is 0, I get k0. And when k2 is 1, I get 2 pi ij divided by 4. Sorry, 2 to the 2. Yeah, so this is the L is 2 term times k1. And it goes on, and then this is the sum here corresponds to the term in this product when it is n. And now we really can see that this is the same thing. Everything we need now is absolutely in these 3 lines, okay? Because this is the square root of capital N. Here, this is the first term, I have e to the 2 pi j divided by 2. Yeah, so j divided by 2. Yeah, no, I didn't need to do a little bit more. Okay, so let's just look at the expansion of j again. So for j is j is this binary expansion. So j divided by 2 is simply, we can forget any integer multiples here because I have e to the 2 pi r. So any integer multiples, that's just going to be a 1. So if I get j divided by 2, it's really just because I don't need multiples of e to the 2 pi r here. It's simply j divided by 2. Okay, which is 0.jn. And in the second term, so let's just observe, let's write that up. Observe j divided by 2 is j1 2 to the n minus 1 plus jn minus 1 plus jn divided by 2. And all of this bit is an integer. So here it doesn't play any role. Okay, so here with the L is 1 term. This is an integer, and then j14 is j1 2 to the n minus 2 plus jn minus 2.
Wait, shouldn't the exponent go to up to n minus 2 in the first line? Because it goes to, like, I recall you wrote j as the exponents of j going up to n minus 1. So then when you divide by 2, shouldn't they go to minus 2.
Yeah.
Okay. Yeah, it's just that. Okay, thank you.
And so here in the second term, we have j divided by 4. So modulo the integers, that's just 0.jn minus jn. Yes. And so this is a very convenient notation to express this product here. And we're done. Now, this is looking like something very familiar to us. It's like something we might be able to think of a quantum circuit which can compute that. So that's the idea now, is that using this theorem, using this expression here, we'll be able to, instead of having an exponential number of gates, which we would need in a classical circuit, we can make a quantum circuit which can compute this in a polynomial number of gates. Okay, so that's the challenge. Let's see how we get along with that. So we've got the bottom decimal point thing, and I'm going to write up here the definition of these gates which will allow us to do these transformations. So let's think how that will be. So this is going to be a diagonal matrix which puts this phase factor into the second term. Okay, so this is going to be 1, 0, 0, e to the 2 pi, pi. And then here we're going to have, oh, sorry, what's on pi? Divide that by 2 to the k. Okay, so this means that R1, if we've got R1 here, that's 2 divided by 2 e to the pi I, which is minus 1. So I'll have 1, 0, 0, minus 1, which we know is our favorite Z. R2, here you get e to the pi I divided by 2, so that's I. This 1, 0, 0, I, this has got a special name, that's S. And we already saw what happens, this pi I divided by 4 here, which is called confusingly the pi divided by 8 gate, and that we used in our discrete set of universal gates, approximation. Our discrete set of gates, which was the T. And the other thing we need to recall is that if I draw this circuit, which we saw right all the way back in the introduction, and I'll allow you to verify as an exercise, this series of 3 T-knot gates is swap. Okay, so that will just simply interchange the two numbers. So let's leave that on there, and let's see if we can come up with it. Just so that you don't get too disheartened by all of this, and what's the point of doing this fairly ugly looking Fourier transform, is this will allow us at some point today or Thursday to find a fast factoring algorithm. Okay, so that's the overall objective here. So if you remember, we looked in the introduction at the problem of factoring, so just factoring a very large integer, and we looked at the decision problem, and it is there is no known polynomial time algorithm to solve that decision problem. And what we're going to do is find a polynomial time algorithm which allows us to solve it if we have a quantum computer. Okay, so that's, and you may well have heard of like quantum computers, which can now factor on is 15 and things like this. And we're going to see exactly how that's done. That's the idea. And the idea behind it is to use the quantum Fourier transform. Okay, so bear with it. It's going to be workable. The intermediate step is the order finding algorithm. Okay, so first we're going to define a circuit which allows us to implement the quantum Fourier transform. Then we're going to think of an algorithm to solve the order finding problem, and from that, an algorithm which will allow us to do factoring. Okay, so that's the right plan. Because essentially the idea being, with the fact, I mean, if you think about a classical Fourier transform, what it's trying to do is think out the periods, the periodics of the sines and the cosines. So it's the same, in a way it's not surprising, it's the same kind of thing. So you're trying to find orders when you have periodicity. In our case, it would be the integers modulo n. Okay, so let's think. So we're going to think of a circuit for this, yeah? So this will be a circuit for the quantum Fourier transform. As ever, we're going to have our input bits J1, J2, so I suppose. Well, I can draw a line because afterwards I might need to write some stuff out. And let's start at the bottom because this is going to be a rather simple one. Okay, so let's look at this quantum bit. I know it's the first quantum bit, but I'm going to put it on the last wire. Okay, so, and what do I need here? I need to I need 0.jn, which is jn, which was jn divided by 2. Okay, so it'll be jn divided by 2. So 2 pi jn divided by 2 would be our no. Okay, yeah, of course. So let's think about that. So what does that look like then? If j is 0, this is just 0 plus 1. Yeah? So let's just look at this. So say if j is 0, then this is basically this is 0 plus 1, which is. Can I write a root 2 on it? Just so that it's correct, yeah, because I've got a 2 to the end. I basically got root 2 to the end here. So we're going to imagine each one of these root 2s is under each one of these, there's a root 2 under each one of these terms. So if j is 0, then here I've got 0, I've just got plus, and if j is 1, then this is 0, j is 1, so this is a half here, and this is e to the pi I, which is minus 1, so this is 0 minus 1, which of course is minus. So what we've got to do in this wire, let's do it again, is a hang-on. And we take 0 to the plus and 1 to minus. And down here, then we will get 0 plus e to the 2 pi I 0.2n. Wow. Good. Right. So here we've got the 0.j minus 1. So now we see how to get that. Well, all we need to do is come along here and put a hand on it. That will give us the 0.j minus 1. But we've got the 0 Jn to do as well. So how do we get this Jn? So this will be Jn divided by 4 here. So that will be an R2 here. So I need to get an R2 coming from the Jn so that we can do a controlled R2 from our M1, which will then apply this R2, I multiply the phase by 0.0 Jn, and then since it's exponential, we have to sum the exponents, and this will give us 0 plus e to the 2 by I 0.Jn minus 1 Jn. I'm going to divide by something, this will be an adjustment. Is that clear? Yeah, so how would I do J2 now? I mean, bearing in mind J2y then, I want this to end on 0 plus e to the 2 pi I 0 point. This starts with J2, J2, J3, Jn. Well, it seems logical that I think it will be an H first, then I'm going to need an R2 going down to the J3 wire. So here I can have an R2 going down here. And then I'm going to need R3s. So let's just do some dots here until we get to the R n minus, would it be n minus 1? No, the R n minus 2. Because this 2 goes from the 3 wire, so this n minus 1. This is going to be n minus 1. It's going to be n minus 2. Can't read that. And here, just got room to stick in an R n minus 1. I'm just going to go down to the J. Okay, and with these two control, I end up sticking on the final two decimal places here. And so finally, to get this 0 plus e to the 2 pi I 0 J Jn. I'm going to need to start off with a Hadamard. To get the 0.J1 then, I need to put an R2 again, but now going down to the to get the 0.0J2. To get the 0.0J2, and then there'll be an R. Let's just do dots at the end. So some dots. So this will be R minus 1 coming down here, and finally and out here. Now that's almost done it. The only problem, and this is why we introduced the swap gate up here, is it's all the wrong way around. This Jn is coming at the end, and it should come first. And likewise, this term should come here, and this coming at the beginning. So now you just follow this, so this is now being followed by n divided by 2 swap gates. Okay, so you simply, with the highest wire and lowest wire, you would have a swap gate here, and then the next one's here, except for a bunch of them. And why should we get excited about this circuit? Well, let's work out how many gates we've got. I mean, that's roughly like we've got n choose 2, right? So we've got the sum of, we've got n plus n minus 1, all the way up to 1, so 1 to n. So it's this is roughly, so this is, well, in fact, n plus 1 choose 2. And then each one of these has got 3 peacock gates, so rough 3 n divided by 2 gates. So order n squared. Now, we will actually need the inverse Fourier transform. So now we have a circuit for the Fourier transform. Now, it's one of the exercises to make the inverse of this. Okay, so if you kind of think you just want to get everything back to how it was at the beginning, that's a very big hint of how you might want to construct the inverse, the circuit for the inverse Fourier transform, which we are now going to use in our phase estimation circuit. Okay, so that's going to be our next step. So I'll just leave that up there for a second more. Right. So there's our lovely circuit for our quantum Fourier transform. And this is now 5.2 phase estimation. And the idea here, so let's suppose U is a unitary operator with an eigenvector U with eigenvalue. Now it's a unitary operator, so its eigenvalues are of the form e to the 2 pi I for some. Fine. And the idea here is that we want to, so pi is going to be some kind of like decimal number, or we can think of it as a binary decimal again, not binary decimal, you know what I mean. So we want to get an estimate for phi. So we want to design a circuit which will give us an estimate for this phase. Okay. Possibly, let's just, I suppose we could just draw it up and then talk about it. I'm trying to think if there's a good way of doing it. So our idea will be at the end to apply the inverse Fourier transform and go back from here and try and get our j's. Okay, so we want a circle which, in a way, at the end of here gives us our phi's, also like I keep saying decimal expansion, but it's decimal over the binaries. I don't know how to say that. Binary expansion for phi here, so that we can then apply the inverse Fourier transform and get what will essentially be an estimate for phi, because here we can only go to a certain number of bits depending on how many wires we put down. Okay, so it will depend on how many wires we use as to say an estimation for our phi. So let's see if we can use this a little bit. So yeah. So I'm going to have to get rid of them because I'm going to need space at the bottom to put the use circuits in it. We'll see. Right. So let me just copy this up. I think it's the easiest way. I'm trying to be clever. But I can't think of a way to do it. So here we're going to have t qubits, and this is going to give us a level of our estimation for phi. We're all going to start off in 0. And here below, I have U, which is our eigenstate, and that will be on some amount of wires, depending on how many qubits you add. Okay, so this is. So what's going to come out the end of these wires is U, because it's an eigenvector, so doesn't get changed when we get to phase. And here we put everything into superposition straight away. So
Maybe what is the U to the power 2 to the? Can you repeat that again? Or
here,
yeah, but like what are these U's in sequence?
so this is the U. So U is the unitary operator.
Yeah.
Okay, so this is U to the 1. So you apply U to.
Oh, it literally means apply U once, then apply U twice, then.
Yeah, then 4 times, and then 2 to the t minus 1 times.
Oh, okay, okay.
I'm going to sidestep the question of how this is actually done until later. Okay? I will mention that in a specific case, okay? Because it's not obvious how you would construct U to the 2 to the t minus 1 in an efficient way. Okay, so what happens if here I do a control U? What happens at the other end of this wire? So this circuit has an input. What's the input of this? So the input is is all t zeros. So we're putting in t zeros, and then there's u. Okay, so this is the input. And it comes here, and we're going to do a controlled u on this final bit here. Sorry, yeah, control u on this. So this will then apply u here, capital U, if this bit is set to 1. So this is now in good position, so I have 0 plus 1. The 0, nothing happens to it. If it's got a 1, it applies u here. But what's u times u? Unitary u times eigenvector u. Well, it's an eigenvector with eigenvalue. It's just going to be that. So here I get e to the 2 pi phi. Well, and now here I do the same onto the second wire.
Wait, why does the first wire give that? Like, if that line is the control bit, why would it change? Like, why would the first result of the first wire not be just Hadamard of 0?
So this isn't 0 plus 1, right? So just ignore everything else and let's just look at this. This is the last cubic, yeah?
Yeah.
So 0, well, 0 doesn't do anything. And the 1 u, well, that implies u.
Wait, but like, why is the result of that wire just 0 plus 2 to the pi I phi 1? Like, the result of the first wire, like, why would the result of the first wire change?
Okay, what happens? 0 doesn't do anything, right?
Okay.
Second one's 1, so it applies u to the second here, right? It applies u here, well, that's multiplied by this.
Yeah, okay. Oh, okay. And the phase is
The phase is coming from the u, but
right.
it rotates. No, the phase doesn't matter if it's here or here.
Okay, so up to global phase, you can just think of it
Well,
as
it's not global phase though, because it's not global. Right? It's just
but like why like is the first like are we sure that this is how it works? Like does the phase that exist because we just applied the u go to the first qubit? Like how like why are we sure that this factor just goes to that wire instead of stays down below, for example?
no, because this when the circuit sees 0 u, it doesn't do anything. It doesn't apply this. It's controlled by whatever this bit is. And when it sees 1 here, it says, okay, now I'm going to apply u here. So I've got 1 capital U. Capital U is this. So I've got 1
Okay.
divided by u.
Oh.
Yeah, and it doesn't, I mean, it's the same on it's the same thing we saw before, that this is equal to this.
Yeah, but like it seems really weird because it's like this the first wire is acting as a control bit, and then but acting as a control bit changes the value. Like
Yeah, I know it's really weird. It is weird, but it works. It's clever. That's what it is.
like that's what
I'll leave you a minute to think about it. I'm just trying to work out.
it shouldn't change. Like like I get, like, mathematically I get that it's equivalent, but it's acting as a control bit and its expression changes. Like, that's what bugs me.
Yeah, I know. It should bug you, but it's rounds. I mean, it's essentially this. This is the key observation, which we've seen before. Yeah, I agree. It looks like it's controlling what's going on down here. But, yeah. I mean, you agree, right? I mean, it's one, so to apply to you here. To apply to you here, it's just multiplied by this. So we multiply by this. Here, well, that's the same as moving it in front.
Yeah, but like this moving it in front, like, does it physically work like that? Like this, I mean, like it ends up being as that times the u, but like I still can't get around the fact that like it's not being acted upon and it still changes.
Yeah, because it's the whole thing that's changed, right? It's all yeah. Think of this as just one qubit. It's both qubits that have changed. Yeah, so they're two qubits together, aren't
Hmm.
they?
One question. It's listener, but
Sí,
shouldn't there be one un entre raíz de dos? The Hadamard gate doesn't perform like, I don't know if yeah, when you perform the Hadamard gate on 0, shouldn't there be an 1 over square 2?
Yeah.
Okay.
Yeah. Yeah. Okay. Sure. Okay, so we'll let Adrian worry about that. And here, of course, then we control it all the way up to this final one, which so let's suppose we know that the expansion for this is 0.01. Sorry, 501, 502. So these are the binaries. Yeah, so this is the binary. So this is a the binary expansion. As a bit, we have because this would be I value, it was e to the 2 pi I 5. Okay, so this is some kind of like number less than 1. So it's like this, and let's say this approximation. So this is the approximation to 2t bits. So let So 2 to the t minus 1 times this phi is 0.52. Modulo z, if you like, up to integer. So if you're getting that integers. So what you could say is, in fact, it's better for us, isn't it? So if we now look at e to the 2 pi I, 2 to the t minus 1 phi, this is precisely e to the 2 pi I 0.5t. Because the integers disappear with the e to the 2 pi I. Likewise, 2 to the, let's say, what's forward go, but we'll down here, 2 times pi is 0.0202. So precisely e to the 2 pi I 2 times pi is e to the 2 pi I 0.
Wait, the phi with the bar, right? With the squiggly.
Oh yeah, thank you.
And then up there as well. No? And the one above. Like 2 to the t minus 1 times psi equals.
Yeah. So what we have here, when we do our inverse Fourier transform, so if we now apply inverse QFT, we get an approximation for I'm just trying to see if actually we do not get no approximation. So if I inverse transform to the first t bits, we end up with basically this. Yeah, it's not quite, is it? Because this is most definitely phi, and not phi twiddle. But phi and phi twiddle are very, very close to each other. Yeah. So but it's still an approximation. So where's going to get approximation?
What in what way do we get an approximation? Like if we do the inverse Fourier transform of this, what do we get? Like,
Well,
oh, okay, we get straight up like phi 1. We get phi tilde, like, or it's like otherwise then it's not an approximation for phi bar, right? It's an approximation for phi because we get phi bar exactly.
right. In fact, we get quite exactly. No, but I'm not sure about that because I mean this is really phi again, right? This is
right. Okay.
I mean it's a close approximation. Maybe I should call this something else. And I get this is now phi hat, which is an approximation for phi. So approximately phi. Yeah, but basically it's an approximation to phi Twitter or phi.
And y next to the y multiplied by the u.
Sorry?
Why would we multiply by the u?
No, this is just still there. This is just down here.
Oh, when we apply the inverse.
Yeah, just
Okay.
no, we don't trust these few bits down here. We just apply the quantum inverse quantum Fourier transform to these wires here, to these qubits here. Now, there's a big discussion about how good this approximation is in Nielsen-Chuang, which I'm not going to go into. But if you want to have a look at pages, the relevant pages, Nielsen-Chuang is 223 to 224, where they discuss exactly how good you can make this. And obviously, the important thing is, and I think it's fairly obvious, if we take more t's here, the better our approximation is going to be. Okay, so the more decimal places you take, the better your approximation. Because the real issue here is not the fact that you're going to get some approximation. The real issue, how good your approximation is, because that's going to be something that you can kind of make better. The real issue is if I give you a unitary operator, you don't necessarily know, we won't know, in fact, what the eigenvector is. Then that is an issue, which we will now deal with. I've had some motion. Okay, I'll just leave that up on the board, so I'm going to clean the board, so I'll just give you a couple of minutes to let myself have a breather. Right. And this thing is, for me, the clever bit. So, problem. We don't know. So let's imagine though that we could know a linear combination of eigenstates. So suppose, let's say US are eigenstates of U, and we do know some linear combination. And as we shall see, now order finally, I'm just going to what do we call it? Phi? Is there any reason to call it phi? Probably not. Then the phase estimation give us after applying the inverse Fourier transform, we're going to get the sum of CS. Let's put it 5 12. Where? The phase the eigenvalue of US. Okay, so yeah, everything's linear, so we stick into our circuit, and then we do everything.
Right. What does it mean that we don't know U? Like it has multiple. Oh, if we have a general state in this basis, then this is what we get. Or like, why do we like? Why is this concept of we don't know U important?
Because in the application, the one I'm about to show you, I mean, in general we won't, and certainly in order finding we don't. But we do know a state which is a linear combination of other states to begin with.
Okay.
So we can start with that, we can stick it into our phase estimation circuit, and we get this. Okay?
Okay.
And now we do a measurement on this. So if we now measure the first, so these would be on the first T qubits, right? So we measure first T qubits and get with probability yes. Yes, yeah, so if you think about what these are, right? These are just strings of zeros and ones. So if we just measure in the computational basis, we get this particular string, this S. So this is still summing in S with a probability depending on this coefficient. Okay, so it probably will be very helpful to look at the example. So let's do an example, and then hopefully things will become a bit clearer. So now we're getting to the exciting bit. So we might not quite get to factoring today, but we will certainly, this was already something very practical so that you can really get a grip on. So here we go. So let's say we're given X and capital N. The maximum common divisor, so they're co-prime. So we want to find so find R such that X to be R to 1 modulo F. Now, of course, we know from Euler's theorem that X to the phi n is equal to 1. I'm going to write modulo N like this. Yeah? Modulo N. Oh, no, just implementation. Where's phi n is the closure number. Okay, so this is the number of integers between 1 and n minus 1, which are co-prime to n. Okay, so 5 of 15 is 8, for example. And I will leave it as an exercise for you to prove Euler's theorem, if you haven't ever proved it before. So we're trying to find, so we know that this R, so this is got to be less than, this is less than or equal to 5. Which is less than n. Right. So we need to work on a quantum circuit which allows us to go at least past this n. So we're going to be choosing L, so choose L. Right there. So bigger than so I want n. Sorry. So choose that. So, okay, and so now we define our unitary. So u of y is just going to be y for so I'm going to have a circuit on L cubes, right? So well, probably maybe a few more, but and for this, we're just going to multiply by this. Now, let's see if we can work out some eigenstates of U. Okay, so let's say some non-trivial ones, because these y's are obviously eigenstates. With the possibility of have something to do with our R that we're trying to find. What happens if I look at this here? Actually, something, isn't it? Okay. What was, let's presume just, okay. What I claim this is an eigenstate of U. So what happens if we apply U to this? Let's see what happens. Well, all these x to the k modulo n's will be less than n minus 1. So when I, by linearity, apply U, I have to multiply here by x. So I get 1 divided by this, none of this changes. And here I get x to the k plus 1 modulo n. Well, this is the sum. So this here goes from 1 to r. So this is the value going from 1 to r here of beta minus 2i s. And now I get k minus 1. If I want to put next to the k, it's just to do change of the sign thing here. So that here I went from 1 to r, now I went from 1 to r, and this was 1, this was 0. So this is 1, this must be 0. Okay, so that's exactly the same.
We were not dividing by r anymore, or the exponent?
Thank you. So now I'm just going to take out this e to the 2 pi I s over r. So what I've done there is I've just taken this bit here in front because it's got to do with k. And now, of course, when k is r, that's exactly the same as k is 0 because this is an integer. So this sum is simply 0 to r minus 1. Because also x to the r, of course, is equal to 1. So this is the 2 pi I s divided by r g s. So let's just think a second what this means for us. I mean, if we knew US, which we don't, but if we did, we could find out, kind of. Well, we could find out an approximation S divided by R. Okay, so our view as well is we well understand it. We've got X, we've got capital N. We can make a circuit between them and U. Okay, so that's okay. And of course, and now I'll touch on the fact that in our phase estimation algorithm we had u squared u to the 4 up to u to the 2 to the t minus 1. And you can see that you can continually squaring here. So there are classical algorithms which allow you to classically square in some polynomial of the log of the number of bits. So I more or less won't go too far into that, but I will touch on it again when we do factoring. So I'll talk a little bit more. I'm going to slightly sidestep that issue again. Well, as I said, we don't know. We still don't know US, and it's maybe not as impressive as it might be. But now it becomes as I said before. There's still two problems, in fact. Firstly, just because we've got an estimation for S divided by R, does that allow us to calculate R? That's one issue. And another issue is we still don't know what US is. But what happens if we sum US from S goes from 0 to R minus 1. So let's do that here. So what would happen if we looked at the sum, let's normalize it. S is 0 to R minus 1 of U S. And you can see that we're going to be summing at some point complex alpha-function of unity over all alpha-function of unity. So we know that this is going to be 0 a lot. So let's see what happens. We get 1 over R, the sum K 0 to R minus 1. I'm going to switch the sum straight away because there's one thing we learned to do at very early, which is switch sums. I don't know. Okay, so that's just fitting in the definition of US and switching the order of the sums. So as I say here, if this K is non-zero here, when I sum over this from 0 to R minus 1, and this doesn't have anything to do with S, right? So this can come now, if you like, this can now come to the other side of the sum. So I get 1 over R sum K x to the K mod n. And here I get the sum S is 0 to R minus 1 of, for the most part, distinct R-rooted unity. I mean, unless this K is 0, this is just going to be 0. So here we have 0 unless K is 0. In which case, when we have K is 0, which we have 1, we're summing we're summing 1 R times. So completion, this linear combination of eigenstates is precisely what you get when you take K is 0 in this sum. And K is 0 equals this 1. And we get the R's cancelled because you've got 1 divided by R here and you have R coming from this sum. And we know how to prepare this. We know how to prepare this state. So we're ready to rock and roll. So we will get, so now let's recap here. We stick this state into our phase estimation algorithm with our U, which was fairly simple, which was just this one where you multiply by x each time. We apply our inverse Fourier transform, it will give us an estimation for S divided by R for some S. Okay, so let's mark it down. So we put U equal to 1 in the phase estimation, phase estimation circuit. And we will get an approximation for S divided by R for some S. Yes, the answer in English. Now, as I mentioned before, the T which was going to give us how close our approximation is, we can choose arbitrarily. So we can choose, we choose t large enough. So that we're guaranteed that let's call this estimate. We're going to approximation, let's say alpha for estimate that. So that that's sort of a bit of random expression, approximation that I'm asking you for. So we can put as many quantum bits for t, so that this approximation gets down to something less than this r. Well, we don't know what r is, but we know it's as low as n. So we can make this to n squared, which is less than to r. Okay.
Wait, what's alpha and S over R, or how does? Like, what do you?
This is the approximation that we get from our phase.
Oh, okay. I didn't read that part. Yeah, okay.
I changed the bets. I don't know why. I think because phi was phi twiddle was just too annoying. Should I put phi twiddle?
No, alpha is fine.
Yeah. Okay. So there's just, and the reason we want this lovely expression because now it's a theorem which goes. I have to admit I didn't know, and I was curious to find out because it then led me to write exercise 3. So then there's a theorem that continued fractions theorem implies that S divided by R appears as a continued fraction of alpha. Okay, so I will now explain to you what continued fractions for those that don't know. And also that there is a order log n, so order n, which is log n, number of things. Well, you'll see that what exactly what I mean. So I'm going to do this by example. Okay, so I want to. So there are examples that there are, let's say, using this n, so there are, this will give or log n possibilities for r, which we can check. X to the r modulo n to discover which is the correct. Okay, so use the so if I give you some alpha, which will be a fraction, you can then deduce. Yes, there are the limited stuff. There's this number of left from log n S divided by r's, which and then you can you go through the r's and you work out which one the r is, which is the order of x. Okay, and that's the idea. And so we will see when we do this continued fraction, when we calculate continued fractions, we can do that very quickly as well. So there's a nice order log n cubed steps or something, log n squared. But we will see it now, because we'll do it now. Okay, so Let us suppose, well, I've done some, so let's suppose alpha is 0.42188. So in our bits, we've got point, this is base 10, and this is it in base 2. Okay, and this is then 54 divided by 128. Okay, so I've done this for 7 decimal places. So that achieving, I think, was it 2t plus 1? To have this approximation. So how do I work out what these s divided by r's are? Well, what you do is you invert and then divide 128. Well, first thing, I suppose we could be sensible here and just actually divided by 64. And now we're going to invert and divide 64 into 27 by 27, which is going to be 2 plus 10 divided by 27. Okay? These numbers don't look at all familiar because I think before I didn't bother doing the and now you continue this way. So this 27 by 2 is 1 divided by 27 divided by 10, which is 2 plus 7 tenths. I'm just going to continue. Let me continue down and I'll tell you this. 2 plus 1 divided by 2 plus 2 divided by 7, which is 1 plus 3. Oops. And you can see the numbers here going down. 10, 7, 3, 12. And now it stops. Because when I get down to 1 here, of course, when I invert it, it's already done, if you know what I mean. Right? I mean so so when I stop it, this then finishes when this numerator gets down to 1. So it's 10, 7, 3, and 1, because now if I try to split and invert that, well, I'll just get the same thing. Right? I'll just get 1 divided by 3, 1 divided by 3, 3 divided by 1, which is 1/3. Okay, so that's just going to go to the final number set to get down to there and it stops. And now you can get the approximation. So you take these fractions and you approximate them to 0 or 1, depending on if they're big or small, 5. So our continued fractions are 1/2. Here I get 1 plus, 1 divided by 2 plus 1 divided by 2 plus 1. Okay, so that's 3. That's 3 thirds. Here I get 1 divided by 2 plus 1 divided by 2 plus 1 divided by 1, which is the same as that one. So that's also 3 seconds. Because with 3 seconds I approximate to 0. And this final one is 1/3. I eliminate this is the 0 now, and so this approximates to 1 divided by 2, 1, 2 divided by 1 plus 1 plus 1 half, which is 1 divided by 2 plus, so here I have 2/3. Here I have 6, 8, 3/8. So this is 8 19ths. So R is either 2, 7, or 19. So then you just take the denominator and you forget about the numerator.
Wait, why does the second approximation, like, shouldn't it stop at the 2? Like, why do we have the 1? Like, we keep making, like, the continued fraction with, like, only 1, 2, then 2 and 2, then 2, 2 and 1. Like, doesn't it stop at the last number? Like the plus 1 shouldn't be there for the second approximation?
Yeah.
No. Like, in the approximation, like, in the box, like, below. Like here, yeah, like the second one, the first 3/7. Like, why do we have the plus 1? Like, shouldn't we just 1 divided by 2 plus 1 divided by 2? Like, if we were just approximating by, like, the continued fraction, like the sequence is 2, 2, 1, 2, 3.
I don't know. I did not know to do that. This would make sense that this would be 1.
No, not there. Like, that's not, no, not there. Like, here, like, and when you have like 1/2 comma something equals 3/7, like in the first 3/7, like, why is the second approximation 3/7?
This one?
Yeah.
Because the 1 divided by 2 plus 2, and I approximated this. I think it may look quite good about it.
Okay. I thought like you were making the approximations as like truncating the continued fraction sequence.
No, I also round these things up and down, but I'm not sure. You might be right. Maybe you're right. It wouldn't matter. All it means is that you get a larger set of approximations. But yes, maybe you're right. Maybe it should be. So in which case, this second one would be 2/5, no?
Yeah.
Yeah. Okay. Yeah. Because that's why I then repeated it in the next one, because I do these approximations to get a better approximation. Because I was thinking, well, it's obviously better if something like this was 0, you're better than 1, that's what you do it next. Yeah, I'll check that. So okay, well, then we get an extra possibility. Now you should be all screaming, right? Because this really is an approximation for S divided by R, and maybe we got unlucky. Maybe we got unlucky because this S was some number between 0 and 1 and R minus 1, and it could have been that we got when we did the measurement, we would get anyone with the probability equally probable. So we might have been unlucky and gotten an S which has a common factor with R. Okay, so we have to it could be, recall, let's see if we've got a better pen. Recall that we got an approximation for S divided by R. And if we are lucky, we got an S it was not co-granted that. I mean, this could really happen if they say R could be like, could be 2, it could be very composite. Yeah, it could, we don't know. Yeah, so we have to rerun. So the idea is you run it a number of times. Okay, so you will know, of course, if it failed, because when you go through your list of possible R's and you calculate x to the R and you don't get 1, then you know something's gone wrong. Okay. So if something, so it's possible it doesn't work. So it's possible that none of the R's work. Is the order, and we must apply the whole thing again. Okay, so we rerun the phase estimation algorithm. We measure again, and this time, if again you've given, I mean, it's even if I was super composite, you're still only gonna. I mean, let's say, yeah, it's possible, I suppose, that so that what would be the worst case scenario? N was twice the product of loads of different primes, then R was the product of all of those primes, and then and then it could be half, couldn't it? But even then, if you run it 3 times, or 4 times, very, very quickly becomes in your favor, even in the very worst case. Okay, well, I've now been talking for an hour and 50 minutes without stopping, barely stopping. So maybe I'll call it a day there. Has anybody got any comments, any questions about this? No? Okay, so let me just say where we're going from here then. So now we're going to use this order finding. So now we have an order finding algorithm, which is we can efficiently run on a quantum circuit. So that means that for our capital N, we can do it in polynomial in the logarithm of n. Okay, so everything here, I mean, this is logarithm n squared, and the worst bit is when we have to do the application of the u squared, u to the 4, u to the and that's order logarithm n cubed. So we're going to use that now on Thursday to come up with a quantum factoring algorithm. So, and actually that won't take us too long. So that's going to be next step. We'll follow that with showing that we can. So that's dangerous, right? Because if you can factorize big numbers, you can break RSA. So I'll quickly recap what that is on Thursday, and then we'll see the other big cryptographic problem, which makes Diffie-Hellman secure and all of these things. The discrete logarithm problem. We will then show that we can also solve that one on in a polynomial time algorithm quantum circuit. So things are looking bad for cryptography as soon as we have a quantum system. But we will also look at some point some very basic crypto systems that you can involve in quantum, which will be secure even on a quantum circuit, even if your opponent has a quantum computer. And that will then just leave us the other type of algorithms. So these algorithms are all built on the quantum Fourier transform so far, and then we will look at something which is completely different. And that will be that. So that will be Grover's algorithm, which is kind of like we saw like a toy one in the Deutsch-Jolles algorithm in the introduction. Okay, so that's more of that style than the quantum Fourier transform that we've seen today. Okay, so I hope I managed to convince you that it's a very interesting thing to look at. Yeah. Okay. So I'm going to stop the